Hello there, Mr. Sutton here, bringing you the BC Calculus 518 Extra Practice Number 2 solutions on improper integrals. For this problem, I'm trying to take the definite integral from 0 to 1 of this expression. Now, this is a little bit tricky because you might notice that the square root of 0 down here is going to make this thing undefined because you're doing 1 over 0. So because we have a discontinuity at 0, this is an improper integral, and we have to evaluate it using limits instead. So I'm going to rewrite this. I'm going to write this as the limit as a approaches 0 from the right side, because we're approaching from inside the integral, of the integral from a to 1 of that stuff that was inside there. So I've basically just rewritten this so that instead of actually having 0 as a limit, we're only approaching 0 from the right side as one of our limits of integration. And now taking the antiderivative, this is really x to the negative 1/2 that we're dealing with, so that bumps up to the positive 1/2, and then dividing by that we just have 2x to the 1/2, and that's evaluated from a to 1, limit as a approaches 0 from the right. So now I can rewrite this as 2 times, and now I'm going to have the square root of 1 minus the square root of a inside there. Well, square root of 1 is just 1. Square root of a is a approaches 0, the square root of that is also going to be 0. And note that we're approaching 0 from the right side, so we're only square rooting positive values on our way to 0 there. So we have 2 times 1 minus 0, which just ends up being 2. For this problem, I'm trying to take the integral from 0 to infinity of e to the negative x dx. So this is an improper integral with this infinite limit. I'm going to rewrite this with a limit. So I'm going to do limit as b approaches infinity of integral from 0 to b of all that stuff. And now I need the antiderivative, so that's going to be negative e to the negative x, evaluated from 0 to b. Still have that limit as b approaches infinity. So now plugging in b and 0, I can write this as negative 1 over e to the b, and then minus minus, so plus 1 over e to the 0, or negative 0, but that's just still 0. Now, as b approaches infinity, this first term is a bottom-heavy term, which means that it's going to go to 0. This second term, e to the 0 is 1. 1 divided by that is 1. So this is just 0 plus 1, which comes out to 1. For this problem, I'm trying to take the integral from 1 to infinity of 1 over x cubed. I'm going to rewrite this using a limit since it's an improper integral. So let me rewrite this as limit as b approaches infinity, integral from 1 to b of 1 over x cubed dx. Now that I've done that, I can just go ahead and take the antiderivative and evaluate it as normal until the very end. At some point, I'm going to have to deal with this infinity. So this is really x to the negative 3. That bumps up to a negative 2 power. Dividing by that, I have negative 1/2 x to the negative 2, evaluated from 1 to b, still with b approaching infinity. So rewriting this, I can yank that negative 1/2 outside, and inside I'm going to have essentially 1 over b squared minus 1 over 1 squared. So as b approaches infinity now, this 1 over b squared term goes to 0 because it's bottom heavy, and this other term here is just going to be minus 1. So we have negative 1/2 parentheses 0 minus 1. And then, let's see here, this is just negative 1/2 times negative 1, which is positive 1/2. On this problem, I have an improper integral with this infinity in my limit of integration. So I'm going to rewrite this using a limit as b approaches infinity of integral from 1 to b of all that stuff. And now just using my reverse power rule to take the antiderivative, this bumps up to a whatever this plus 1 is. So that's going to be positive 0.01. Dividing by that, well, the exponent's really 1/100th, so you're really multiplying by 100 if you're dividing by that. So we have 100 times x to the 0.01. Limit as b approaches infinity, evaluated from 1 to b. So let's yank out that 100, and inside I'm going to have b to the 0.01 minus 1 to the 0.01. As b approaches infinity, this b term here, I mean, this is pretty small. This is like the 100th root of whatever you're plugging in, so it's not going to grow very quickly, but b is growing to infinity. B literally has forever to get to where it needs to go. So this first term is going to infinity. This other term then becomes insignificant, and this whole thing is growing to infinity, which is to say that this integral diverges and has no value. For this one, looks like we have an issue with this infinity here in the upper limit of integration. That's an improper integral, so we have to rewrite it using a limit. I'll do the limit as b approaches infinity of 1 to infinity integral, or 1 to b integral there we go, of 1 over x to the 1/2 power. Antiderivative here, well, this is really x to the negative 1/2. That bumps up to a positive 1/2. Dividing by that, we're really multiplying by 2. So we have 2x to the 1/2 power. Still have limit as b approaches infinity, still going from 1 to b. So I can yank out this 2, and inside I have the square root of b minus the square root of 1. As b goes to infinity, well, that's a bit of an issue. The square root of infinity is still infinity, so this whole thing goes to infinity, and this integral diverges and has no value. On this problem, one of the limits of integration, 0, is going to give us a discontinuity on this 1 over x squared function because you're dividing by 0. So this is an improper integral because of that. So that means we're going to have to rewrite this with a limit. I'll do the limit as a approaches 0 from the right of integral from a to 1 of 1 over x squared. So now it's not quite like plugging in 0. It's like we're just getting really close to 0 coming from the right side. So now taking the antiderivative here, this is really x to the negative 2. That bumps up to a negative 1. So we have negative 1x to the negative 1 evaluated from a to 1 with a approaching 0 from the right. So this is going to be negative 1 over a. Actually, negative 1 over 1, there we go, minus, or actually minus minus, so plus 1 over a. And as a approaches 0, well, that's a bit of an issue because you're dividing by 0 here. So this does not exist, and that means that our integral is going to diverge. For this problem, I'm trying to take the integral from 0 to infinity of this crazy expression. So there's so many things that are wrong with this. Let's just start with the most obvious. We have an infinite limit, so we need to fix that. I'm going to rewrite this as the limit as b approaches infinity, integral from 0 to b of all that wackiness there. Next issue is, how do you even take the antiderivative here? So one thing that it might be helpful to note is that we have a function, arctan, whose derivative, which is something involving a 1 plus x squared, is elsewhere in the problem. So we might be able to use some u substitution to get rid of all this stuff and somehow untangle this. So I'm going to start by letting u equal 16, or arctan of x. I'll just use arctan of x. We don't even need the 16 there. So then du is going to be 1 over x squared dx, or 1 over 1 plus x squared dx. There we go. Which means if I multiply both sides by 1 plus x squared, we have 1 plus x squared du is going to be the same as dx. And now I also need to turn these x values here into u values. So if x is 0, then u is going to be the arctan of 0. And what is the arctan of 0? Well, that is the angle between negative and positive pi over 2 that has a slope of 0. That would just be 0. And now if x is b, then, well, this is a little bit easier. U is just going to be the arctan of b. All right, plugging all that back in, we have a limit as b approaches infinity of, and now I'm going from 0 to arctan of b on my limits of integration. Here I've got 16u over 1 plus x squared, and instead of dx, I now have 1 plus x squared du. All right, so let's clean it up a little bit. These 1 plus x squareds are going to cancel, so I have 16u du. Same limits of integration, same limit out here. And now I can actually take the antiderivative in terms of u. So this bumps up to a 2 for the exponent on the u. Dividing by that, we have 8u squared, evaluated from 0 to arctan of b, with b approaching infinity. So yanking out that 8, we have basically arctan of b squared minus 0 squared inside. And now what happens is b approaches infinity. So it's tempting, since this is not in the bottom of any kind of fraction, to just say, oh, well, this is going to go to infinity, so this is all infinite and we're diverging. However, you have to think about what arctan is really doing. Arctan takes as its input a slope, and it gives you back an angle. So as the slope of some angle is getting infinitely positive, think of just a slope basically becoming almost vertical. Well, what angle are you approaching when you have an almost perfectly vertical slope in the positive direction? Well, that's like the top of the unit circle there. That's pi over 2. So as b approaches infinity, arctan of b is approaching pi over 2. So we have pi over 2 squared minus 0. We still have that 8 out there. And now pi over 2 squared, that's really pi squared over 4. Pi squared over 4 times 8 is just going to be, well, let's see, 8 divided by 4 is 2, so that's just going to be 2 pi squared. And this 0's gone, so 2 pi squared it is. For this problem, I'm trying to integrate tan of x from 0 to pi over 2. Now, the problem with doing this is not the 0 here. Usually the 0 is the issue, but pi over 2. Tan of pi over 2, that's trying to give you back the slope of this angle. And this angle it's at a perfectly vertical line, so tan cannot handle pi over 2. Because there is a discontinuity at pi over 2, this is an improper integral, which I can only hope to evaluate by rewriting it using a limit. So I'm going to go with the limit as b approaches pi over 2 from the left side, so that we're approaching from inside the integral. So as b approaches pi over 2 from the left of 0 to b integral of tan of x. Okay, that's nice. Now I have to actually, though, integrate tan of x. So how do I take that antiderivative? Well, this will be easier if you rewrite tan of x as sine over cosine, because now we can think of this cosine as being kind of like an inner function in a reciprocal 1 over x sort of situation. And the derivative of cosine is sine, so because we have this situation here, integration by substitution might help us out here. So let's let u equal cosine, and then du is going to be negative sine of x dx, so that du over negative sine of x is the same as dx. We also have to change out these limits of integration, which are currently x values, for u values. So if x is 0, then u is the cosine of 0, which is going to be 1. And if x is b, well, now u is the cosine of b. Plug in all that back in. We can rewrite this as limit as b approaches, still going to be pi over 2 from the left. Now, though, we're going from 1 to cosine of b for those limits of integration. We've got sine of x over u, and instead of dx, we have du over negative sine of x. Sine of x's are going to cancel. We've really got negative u to the negative 1 power. Antiderivative of that is going to be negative ln absolute value of u, still evaluated from 1 to cosine of b. b is still approaching pi over 2 from the left. Now, if we actually plug all that in, we have negative ln absolute value of cosine of b minus, so plus ln of absolute value of 1. ln of 1 is just going to be 0, so that's not really going to make much difference here. But now we have to consider what happens to cosine of b as b approaches pi over 2. Well, at pi over 2, cosine takes on a value of 0, so you're approaching 0 here. And then you have to consider this ln is trying to figure out what's happening as its input is approaching 0. Well, the ln function by itself, as you're getting closer and closer to an input of 0, it just keeps going down to negative infinity. This negative out here probably makes that positive infinity, but either way, this term here is not going to exist, is not going to have a finite limit if b is approaching pi over 2. So because this term here does not have a limit, that means the whole thing does not have a limit, which means this integral diverges and has no value.